Hello, in this video we are going to discuss the following topics: Euler paths and circuits, Hamilton paths and circuit, and the applications of Hamilton circuits. Can we travel along the edges of a graph starting at a vertex and returning to it by traversing each edge of the graph exactly once? Can we travel along the edges of a graph starting at a vertex and returning to it while visiting each vertex of the graph exactly once? Although these questions seem to be similar, the first question, which asks whether a graph has an Euler circuit, can be easily answered simply by examining the degrees of the vertices of the graph. While the second question, which asks whether a graph has a Hamilton circuit, is quite difficult to solve for most graphs. In this video, we will study these questions and discuss the difficulty of solving them, although both questions have many practical applications in many different areas. The city of Königsberg in Russia was set on both sides of a river and included two large islands which were connected to each other and the mainland by 7 bridges. Figure 1 is shown these regions and bridges. The townspeople took a long walks through town on Sundays. They wondered whether it was possible to start at some location in the town, travel across all the bridges once without crossing any bridge twice, and return to the starting point. Can you think which path they should take? The Swiss mathematician Euler solved this problem. His solution, published in 1736, may be the first use of graph theory. Euler studied this problem using the multigraph obtained when the 4 regions are represented by vertices and the bridges by edges. This multigraph is shown in figure 2. The problem of traveling across every bridge without crossing any bridge more than once can be rephrased in terms of this model. The question becomes, is there a simple circuit in this multigraph that contains every edge? That leads us to the following definition of Euler circuit and Euler path. An Euler circuit in graph G is a simple circuit containing every edge of G. An Euler path in G is a simple path containing every edge of G. So let us take an example. Which of the indirected graphs in figure 3 have an Euler circuit? Of those that do not have Euler circuit, which have an Euler path? The graph G1 has an Euler circuit, for example, A to E, then to C, then to D, then to E, then to B, and then we end at A again, as we can see in figure 4. Neither of the graphs G2 or G3 has an Euler circuit, as we are going to verify in next slide. The graph G2 has no Euler circuit because we can visit all edges in the graph only once to have an Euler circuit. As we can see from figure 5, we failed to visit the edges A and E, B and E, D and E, or C and E without touching an edge twice. However, G3 has an Euler path, namely A to C, then to D, then to E, then to B, and then to D, and then to A, and then to B. As you can see from figure 6, the green circle indicates the sequence we take for the Euler path. So we could not visit all edges and return to the vertex A that we started from, and we do not have an Euler circuit, but we managed to have an Euler path. However, G2 does not have an Euler path. We will try to draw the path as shown in figure 7. We go from A to E, then from E we find that we have to go either to D or to B. Let us go into the path D, C, D, A. We find there is one edge unvisited, so we cannot have an Euler path in this graph. So let us take another example. Which of the directed graphs in figure 8 have an Euler circuit? Of those that do not, which have an Euler path? The graph H2 has an Euler circuit. For example, we go from A to G, then to C, then to B, then to G, then to E, then to D, and then to F, and then to A. Neither H1 nor H3 has an Euler circuit. I leave this for you to verify. H3 has an Euler path, namely C, A, B, C, D, B. But H1 does not has an Euler path, and you can try to verify the Euler path of H3. There are simple criteria for determining whether a multigraph has an Euler circuit or an Euler path. Euler discovered them when he solved the famous Königsberg problem. We will assume that all graphs discussed in this video have a finite number of vertices and edges. What can we say if a connected multigraph has an Euler circuit? What we can show is that every vertex must have an even degree. To do this, first note that an Euler circuit begins with a vertex A and continues with an edge incident with A, say A and B. The edge A and B contributes 1 to the degree of A. Each time the circuit passes through a vertex, it contributes by 2 to the vertex degree, because the circuit enters via an edge incident with this vertex and leaves via another such edge. Finally, the circuit terminates where it started, contributing 1 to the degree of A. Therefore, degree of A must be even, because the circuit contributes 1 when it begins, 1 when it ends, and 2 every time it passes through A. A vertex other than A has even degree because the circuit contributes 2 to its degree each time it passes through the vertex. We conclude that if a connected graph has an Euler circuit, then every vertex must have even degree. By the same reasoning, we see that the initial vertex and the final vertex of an Euler path have odd degree, while every other vertex has even degree. So a graph with an Euler path has exactly 2 vertices of odd degree. In the next slide, we will show that these necessary conditions are also sufficient conditions. In the graph G in figure 9, we begin at A and choose in succession the edges A, F, F to C, C to B, and B to A. The path we have constructed must terminate because the graph has a finite number of edges. So we are guaranteed to eventually reach a vertex for which no edges are available to add to the path. The path begins at A with an edge of the form AX, and we now show that it must terminate at A with an edge of the form Y and A. To see that the path must terminate at A, note that each time the path goes through a vertex with even degree, it uses only one edge to enter this vertex. So because the degree must be at least 2, at least one edge remains for the path to leave the vertex. Furthermore, every time we enter and leave a vertex of even degree, there are an even number of edges incident with this vertex that we have not yet used in our path. As we form in the path, every time we enter a vertex other than A, we can leave it. This means that the path can end only at A. Next, note that the path we have constructed may use all the edges of the graph, or it may not if we have returned to A for the last time before using all the edges. An Euler circuit has been constructed if all the edges have been used. Otherwise, consider the subgraph H obtained from G by deleting the edges already used and vertices that are not incident with any remaining edges. When we delete the circuit A, F, C, B, A from the graph in figure 9, we obtain the subgraph labeled as H. Because G is connected, H has at least one vertex in common with the circuit that has been deleted. Let W be such a vertex. In our example, C is the vertex. Every vertex in H has even degree, because in G all vertices had even degree. And for each vertex, pairs of edge incident with this vertex have been deleted to form H. Note that H may not be connected. Beginning at W, construct a simple path in H by choosing edges as long as possible as we've done in G. This path must terminate at W. For instance, in figure 9, C, D, E, C is a path in H. Next, from a circuit in G by splicing the circuit in H with the original circuit in G. This can be done because W is one of the vertices in the circuit. When this is done in the graph in figure 9, we obtain the circuit A, F, C, D, E, C, B, and A. Continue this process until all edges have been used. This produces an Euler circuit. The construction shows that if the vertices of a connected multigraph have even degree, then the graph has an Euler circuit. We summarize this result in the following theorem. A connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. We can now solve the problem of Königsberg. Because the multigraph representing these bridges, shown in figure 2, has four vertices of odd degree. For instance, degree of A equals 5, degree of B equals 3, degree of C equals 3, and degree of D equals 3. So it does not have an Euler circuit. There is no way to start at given point, cross each bridge exactly once, and return to the starting point. We will now show that a connected multigraph has an Euler path and not an Euler circuit if and only if it has exactly two vertices of odd degree. Consider graph G1 in figure 10 as an example. First, suppose that a connected multigraph does not have an Euler path from A to B but not an Euler circuit. The first edge of the path contributes 1 to the degree of A. A contribution of 2 to the degree of A is made every time the path passes through A. The last edge in the path contributes 1 to the degree of B. Every time the path goes through B, there is a contribution of 2 to its degree. Consequently, both A and B have odd degree. Every other vertex has even degree, because the path contributes 2 to the degree of vertex whenever it passes through it. Now consider the converse. Suppose that a graph has exactly two vertices of odd degree, say B and D. Consider the larger graph made up of the original graph with the addition of an edge B and D. Every vertex of this larger graph has even degree, so there is an Euler circuit. The removal of the new edge produces an Euler path in the original graph. Theorem 2 summarizes these results. So what theorem 2 is telling us? That a connected multigraph has an Euler path but not an Euler circuit if and only if it has exactly two vertices of odd degree. Let us take an example to understand this theorem. Figure 11 is showing three undirected graphs which graph have an Euler path. G1 contains exactly two vertices of odd degree, namely B and D. It has an Euler path that must have B and D as its endpoint. One such Euler path is D, then A, then B, then C, then D again, and then B. Now G2 has exactly two vertices of odd degree, namely B and D, so it has an Euler path that must have B and D as endpoints. One such Euler path is B, then A, then we go to G, then to F, then to E, then to D, and then we go to C, to G, then to B, then to C, and then to F, and then to D. But G3 has no Euler path because it has 6 vertices of odd degree. Returning to the 18th century Königsberg problem, is it possible to start at some point in the town, travel across all bridges, and end up at some other point in the town? This question can be answered by determining whether there is an Euler path in multigraph representing the bridges in Königsberg, as you can see in figure 2. Because there are 4 vertices of odd degree in this multigraph, there is no Euler path, so such a trip is impossible. So far we have found out that the Königsberg problem has no Euler circuit nor Euler path, which make it impossible to solve. Finally, I want to show you an example where we can find the Euler circuit in a graph very easily. Find an Euler circuit in the graph shown in figure 12. So what we need to do is to select a starting point. Let's say vertex A is our starting point. We need to make sure that we end at A. So first we go from A to D, and then we go from D to C, and then we go from C to I, then to J, and then to N, and to O, then to K, then we go back to J, then we go back to D, and then we go back to E, and then to K. Now we go to L, then H, then M, then G, then F, then we go to E, then we go to B, then we go back to A, our starting point. So in this video we have discussed in details the problem that found the science of graph theory, the problem of 7 bridges of Königsberg, and we introduce you to the famous Euler path and Euler circuits. Then we took many examples about finding the Euler path and circuits in a graph. Thank you for watching and see you in next video.